Well, welcome back to Physics 3402, the section on scattering and scattering theory in quantum mechanics. I think this is the fourth lecture in a series of 6 or so on this topic, and I want to spend just a couple of moments going back over where we've been to set the stage for what I'm going to be talking about today. So we started off sort of closing the curtain on the first part of what the course was focusing on, which was understanding how to calculate, using various approximation methods, the measurable quantities related to discrete states in the Hilbert space. And what are those measurables? Well, you can measure energies and you can measure spatial distributions. So thinking about spatial distributions, you can measure, say, the fraction of the probability in one state or another, maybe in a left well or a right well, or a tunneling probability, these kinds of things. So the discrete part, the shape of the wave function and its time dependence in a time-dependent case, and the energies of these states are directly physically accessible. Now we've moved on to the continuum, where the energies are continuous, and since all energies are possible, there's not really a prediction coming from the theory about energy, and nor is there anything specific from the dynamics in the theory that's going to predict anything about the shape of the wave function, since the shape is generic and common to all potentials. And we've gone through what that shape looks like. It looks basically like a beam coming in from the left and interacting with the target and passing through the target, becoming the undisturbed beam passing off to the right, but then combining with that an outgoing spherical set of sort of attenuating waves that have the kind of generic shape e to the ik r over r. And since that's common to all potentials, although the details of the strength of those waves differ, most of the gross features that I've gone through so far are common to all potentials. What is it that makes them distinct? It actually turns out that the one distinction is the fingerprint of each potential is in this f of theta. And the f of theta physically is what I'm going to describe using the picture down below here. But let's first remind ourselves what the partial wave expansion says that f of theta can actually be described as. It's a function of theta between 0 and pi, and therefore can be expanded in terms of any complete basis. Let's take the Legendre polynomials in cos theta as our discrete basis. Then, since it's discrete, we have these subscripts L, which are integers from 0 to infinity. We factor out a common term, 2L plus 1, and then the remaining coefficient we call L, and that's just for convenience. These A sub L's are called the partial wave amplitudes, and this set of complex numbers collectively is a complete description of the f of theta and really describes everything we can learn about the potential from experiment. So let's see what experiment is actually accessing and try to make contact with as much of the quantum mechanical description in the experiment as the experiment can reach. And here's the physical scenario for a scattering state. We have not drawn here, but imagine in this white space over here a wave function coming in from the left. It's all plane waves, and it is impinging on a target, which is represented by a potential V of r centered at the origin. We're going to imagine that that's a finite range potential. And if we scale back so that the whole range of that potential is contained inside this little circle, then once the scattered wave emerges from that circle, all the motion from then on is free propagation. For that which comes out of the circle, scattered into all the angles away from the beam. The description is just spherical waves with the radial form e to the I k r over r and the angular form f of theta. Now we'll put the detector here, far away, represented by this shaded box, and facing the target so that it subtends a certain small fraction of the total outgoing spherical wave. And we'll take the detector size to be small compared to r so that we can represent the angular size as seen from the target by some differentially infinitesimal expression d omega. And remember, because it's a solid angle, it's dimensionless, but we mean nothing more than the area divided by r squared. So that's the solid angle. Now, what is the count rate of that detector? Well, the particles that are reaching the detector are embodied inside these waves that are nothing more than de Broglie waves that carry the probability of the particles as they approach the radius capital R that we've placed the detector at. So let's try to quantify the decounting rate in terms of what we know about de Broglie waves. We're going to form the count rate out of two things. We're first going to say how much volume represents the total number of particles that are going to pass through the detector in an amount of time dt. Well, the volume is simply this little representative volume here that you can think of as like a mason jar, where the lid and its cross section all the way down through is given by the area of the lid, and then the height of it is all of the part of this volume in the surrounding space that will be pushed through the detector by the advance of the wave, and these wave fronts, we'll say, are coming along at some velocity, which, since it's free, will be given by the group velocity of the particles in this free medium. Okay, so what's the total volume? In time dt of the particle that contains the particles that will pass through the detector, well, it's the area, which is r squared d omega, and then the height, which is v dt, where dt is the amount of time we're waiting to watch to see those particles detected. That's the volume. How many particles are in that volume? Well, you multiply the volume by the density, and the density is given by psi star psi. Since we're in the continuum, we have to integrate over the entire interior, and for small dt and small d sigma, we can take that density to be uniform and bring it outside the integral, and we have the volume times some number, psi, which we square. And psi is this formula here, so let's square it. E to the I k r becomes 1. This becomes 1 over r squared, and this becomes f squared. So here, now I'm doing putting together all the factors. Particles per second at the detector is volume, which I get from here. I do per second, so the dt moves down and underneath the dn. And then for the psi star psi, I write 1 over r, where now I'm actually using the distance to the detector capital R, and f squared. Notice the factors of r cancel. Furthermore, if instead of just doing detector count rate, I back off and say, maybe I can express things in terms of this cross-section we introduced before. That's dn dt times 1 over the luminosity. And if we divide both sides by this solid angle differential, then the expression becomes particularly simple to express in terms of the geometric quantities above, because the d sigma will cancel with the one on the bottom, and we end up only with f of theta squared v over L. V being here, and the L being in the definition that relates a count rate to a cross-section. What is L? L is the luminosity of the beam back at the target. As it approaches the target, we imagine this e to the ikz incident beam that was part of the scattering scenario we drew up for this quantum description of a scattering state. So if we're going to interpret particles per second from that wave, then we're going to use the same prescription as before. But now it's particles per unit area, so we don't need the r squared d omega. That's the area unit, and that's going to be divided. So all we are left with is the v term, L, where the unit amplitude tells us that psi star psi is 1, because it's just 1 times e to the ikz. There's no f of theta out here. Then L is nothing more than v. This term becomes 1. Notice this. D sigma d omega is just the scattering amplitude squared. So in terms of physical units, f of theta is a directly measurable quantity once you square it. So at least its modulus, not its phase immediately, is a measurable quantity. We're going to find out later that its phase has a different significance. It's also a physically significant thing, but in a different way. So this is the differential cross-section, nothing more than scattering amplitude squared. So you can think basically of the amplitude, of the strength of this wave as it approaches, directly measures the cross-section differential in the solid angle. Now, as kind of an aside, I want to introduce another quantity you'll need for the homework. Sometimes you're asked not for the differential cross-section, but for the integral cross-section, called the total cross-section. As suggested by the name, we get sigma by just integrating d sigma d omega. So here's an integral expression. What's the integral over? It's over all 4 pi steradians of the solid angle. So you form the unit sphere. You then paint onto that sphere this function f of theta. And then you integrate over the entire unit sphere by taking d omega over 4 pi. Now, mathematically, in order to do that integral, we need to insert 2 powers of f of theta. Each power of f of theta consists of a sum over L. So now what am I going to do? Well, I can make 2 powers of L by embedding a second copy of this same expression inside, and then making a double sum, L and L prime, say. Then I'm going to have a factor A sub L prime, one of them starred. This factor will appear twice, one for L and one for L prime, and this factor once for L and once for L prime, but with the same cos theta in both. And of course, before I'm done, I'm going to integrate over that cos theta. Well, the p sub L's are so-called orthogonal sets. What's it mean? It means that if I have a p sub L on one side and a p sub L prime on the other side, with each with cos theta in them, and then I integrate d cos theta, then I get 0. Unless L and L prime are the same. That's the orthogonal polynomial condition. I write that down here. Here again, I'm integrating over the whole solid angle, which represents cos theta going from -1 to +1. And if I have both powers from the 2 powers of f of theta inside, this will vanish unless L and L prime are the same. Here's the exact expression. When I substitute that in, the 2 sums over L become a single sum, collapse down to 1 sum over L, and I obtain something that looks like a sum over the squares of the A's times a wave factor times 4 pi. So whether we're interested in this differential cross-section or the total cross-section, everything resides in these partial wave amplitudes, the A sub L's. What are these? We're going to go more in depth. And the subject of the rest of this lecture is to try to get some insight into the meaning of these A sub L's. And there's a hint already in this, just in the algebraic form of the A sub L's. We will see that the A sub L's can be written in this way. They are complex numbers, but they're built out of a single pair of real numbers. Those 2 real numbers, first of all, are K. Second of all, are this phase factor called delta L. Why K? Well, you know that A sub L has to have units of length. How do I know that? Well, F is a length, because when you square it, It's an area. This doesn't contain any units. This one's an angle. Where does the length live? It's in the A sub L. So that's in units of meters or centimeters or nanometers. The A's have units of length. What's the only constant we have available to us that has units of length? Well, K is 1 over length. So by taking the reciprocal of K out front, that carries the unit. Everything else, including the complex phase, lives in these two terms. And notice, one real number determines both. And so therefore there's a kind of a linkage in between the modulus, we call this factor, and the phase. Both of them determined by a single number called delta sub L. This number is called the phase shift. Each A sub L has a corresponding delta sub L. And it turns out that even though the A sub L's themselves only seem to have any real meaning when you sum them up, the delta sub L's have a real physical meaning one by one. And this is an amazingly intuitive way to view this partial wave expansion. So I want to spend some time emphasizing this. It'll stick with you once you see this phase shift expression. And I think it'll help illuminate what may look like at this point to a fairly abstract mathematical formalism for scattering. What delta L is going to do for us is it's going to make us a connection between the dynamics that lives inside the Hamiltonian and the observables that we see when we measure cross-sections when an experiment. Here's the logic. Start off with dynamics, that is, some idea of what the potential that describes the interaction between the beam and the target might be. That potential predicts scattering phase shifts, as we'll see. Once we have the phase shifts, we use the prescription just described to turn it into scattering amplitudes, sum up the scattering amplitudes times Legendre's, and we get a scattering amplitude function, square that, and we get a cross-section. There's the chain. Okay, so let's now back off and use a one-dimensional quantum mechanics scattering analogy to get some insight into this number delta L and see why it's called a phase shift. Let's imagine a one-dimensional problem in which the potential is 0 everywhere on the left-hand side for x less than 0. For x greater than 0, starting at 0, let's construct an infinite barrier, something like a half-sided infinite square well. What happens? Well, I have free states on the left-hand side and a complete barrier on the right-hand side. So the incoming wave, the right propagating wave, looks like a infinite plane wave, semi-infinite plane wave. What happens when it reaches the barrier? Well, it has to have a node there because the potential is infinite. And the condition for the node is that there is a right propagating wave, okay, of equal amplitude that exists in the same region of space. Physically, you picture the particles coming in, having 100% reflectivity, and coming right back out, moving with the same speed in the opposite direction. Here's the wave function. Everybody knows how to do that. You construct it out of two pieces with equal amplitude, either the ikx and either the minus ikx. By putting the minus sign in there, we assure that we have a node at x equals 0. Okay. The incoming wave, now, in the next section of this discussion, is going to be the same. What's going to be modified, as we'll see, is the reflected wave, but only in a certain way. There's a kind of minimal modification that happens. We're going to tweak the problem by imagining that some section leading up to the barrier has now some arbitrary potential that's non-zero. However, let's stick with the idea that it has a finite range, so that as you come away from the barrier, eventually you reach a point, say at a distance a away from the barrier, where the potential is again 0. And we restore again free propagation all the way off to the left to infinity. Let's solve the same problem. incoming waves, at least if we consider them over here, have exactly the same form. They are pure e to the ikx. They propagate in without disturbance until they reach this point where the potential begins to become non-zero. What happens at that point? Well, not anything immediately. Think WKB. The particle continues to propagate forward, but its wavelength is modified by the presence of the V. So you can think of this as having a kinetic P that's decreased by some of the kinetic energy being absorbed into potential to climb the hill. As the wave propagates in, it looks more or less like the same kind of wave that came incident from the left, except its wavelength is longer. As such, the phase of the wave advances slightly less quickly than it would have in the free case. Once it reaches the barrier, exactly the same reversal happens. There's a flip of sign, there's a flip of the direction of the motion, and the particle rolls right back down the same potential. Whatever phase advance or retard happened on the way in happens in the opposite time order on the way out, so that by the time it gets back to here, it'll have accumulated twice as much phase advance, or in this case, phase retard, as happened on the way in. Then, once it reaches the V equals 0 region, it resumes the same functional form as we had before, going at e to the minus ikx, propagating in the other direction with exactly the same wavelength and, because of probability conservation, exactly the same magnitude of amplitude. So what changed between this? If I can get my mouse to move again. Okay, what is it that's changed between this situation and this situation? Looking, of course, outside the region where the potential is present. The only thing possible if this changed is that there has been a shift of where the wavefronts are. The same amplitude, same wavelength, but a shift of the position of the wavefront. So that as it propagates along, the wavefronts here might be, say, 20 degrees or 30 degrees ahead of where they would have been, or behind, relative to the V equals 0 case. This we call a phase shift. Again, probability conservation forbids an amplitude shift. The wavelength shift is forbidden by energy conservation. Only thing that we can change is the phase shift. Let's now describe this same wave function here in the V equals 0 region and compare what it would be in the equivalent region up here. Up here, it's just e to the ikx minus e to the minus ikx. Down here then, it's of exactly the same form where we apply a phase shift. It's conventional to call it twice the phase shift, where we consider half of it to come, that is e to the I delta to come from the inward bound trip, and the identical amount to come again from the outward bound trip. So as the wave approaches the barrier, it either falls behind its cousin with V equals 0, or it advances ahead of its cousin, depending on whether V is greater or less than 0. Let's see if we can see by intuition which it should be. If V is less than 0, then you've actually got more kinetic energy, and the spacing between the wavefronts is smaller, so the phase advance will be greater. You'll see more crossings between the different wavefronts as you go toward the barrier. In the case where the potential is negative, that means that this phase shift will be positive. On the other hand, if, as we should depict it here, the phase shift is positive, you'd expect less phase advance as it covers the distance and covers it back again. So there's a kind of a physical intuition that comes about by looking at this number, the phase shift. And that is that if the phase shift is positive, we say the potential is attractive, be negative. If the phase shift is negative, then we say the potential is repulsive, be positive. And of course, in the case where V is 0, no phase shift. That's the definition. So the V equals 0 case is the reference wave where you're not looking inside the region, but you're looking outside the region where v would be 0 anyway, and you're asking for a comparison between the actual v that was encountered by the particle and what would have been present if the target had not been there. Okay, so this is phase shift, a reference situation being compared to the actual. Every potential in one dimension has a characteristic set of phase shifts. Notice if I change the energy, then I'm going to see a different value for the phase shift, and the whole map of phase shift versus energy is something like a lookup table that you can invert and figure out what the potential was. That's in 1D. How does this apply to 3 dimensions? Let's try and extend it. Let's go back now to 3D and consider what we do. Well, what we do, first thing we do in 3D, if it's a spherically symmetric potential, is we try to convert it to the equivalent one-dimensional potential. And now let's see how to do that. What we do is write down the wave function as u of r over r times YLMs. Use the YLMs to convert the angular part of the kinetic energy into what looks like a centrifugal barrier potential, and that becomes now an L-dependent potential for the equivalent one-dimensional problem. I'll review that later on, just in case that didn't quite communicate. But we're following the standard thing that we did in the hydrogen atom. We're converting a 3D problem into a 1D problem, where we make the part of the angular part of the kinetic energy as if it were a potential, and moving it into the potential for an equivalent 1D problem, where the wave function in 1D is this u of r. Here's a picture. We end up with a effective potential that depends on L. This is this equivalent potential that has V in it, the original V in it, but it also has the centrifugal barrier in it. Here I've depicted it for some L. See how it becomes repulsive at small distance, like the centrifugal barrier. And even in L equals 0, there's this infinite barrier that comes up just because we've constructed our coordinate system so that r negative is impossible. All right, here's the physical potential. As we come away from 0, we see it's attractive in this little illustration that I'm drawing here. And then, beyond some radius a, I'm going to say the potential is 0. There's my finite range assumption. Potential, centrifugal or not, is 0 beyond some limit. Okay. Now let's set up our continuum state in this one-dimensional equivalent problem. We have an incoming wave. Of course, the u itself is just this numerator. Here's the u of r over r. That's the incoming wave. The outgoing wave is, of course, e to the plus ikr. And it results from the incoming r in this particular L substate, coming in, hitting the barrier, reflecting off, and coming out, just like we saw in the one-dimensional problem. So even though we would, in a full description, have to write it as e to the ikr over r, in the equivalent 1D problem, u is just e to the minus ikr. In and out, e to the plus ikr. Well, that certainly is nice to draw as an analogy, a formal analogy to the 1D problems we discussed earlier. And you can see how a phase shift would come out of such a description. Except here now is a challenge. Where do we get the piece that looks like e to the minus ikr for in a scattering problem? The scattering problem had only two pieces, e to the plus ikz, and the outgoing wave counterpart, e to the plus ikr over r, that's in the scattering spheres that are coming out. So where do we have ingoing spherical waves? This turns out to be something of a sleight of hand, so pay attention here. The incoming wave is buried inside this plane wave. Of course, the plane wave is incoming, isn't it? That's how the particles get to the target. But how does something that looks like e to the plus ikz end up looking like e to the minus ikr? Turns out that that's a really straightforward connection. E to the ikz actually contains inside a piece that looks like e to the minus ikr over r. hang on, because we're going to see how this happens. Raleigh's formula. Raleigh came up with this expansion. He said, here's a function that's written really in Cartesian coordinates, but any function in Cartesian coordinates can be re-expressed in cylindrical coordinates or in spherical coordinates by using the appropriate complete set of basis functions. Turns out that this is a good complete set in R, and this is a complete set in theta. And if I make a product between the two, then I can form a complete set in their joint distribution. And all that's left is to determine these coefficients that go along with the sum. And so again, our friends, the spherical Bessels, here's the YLMs for m equals 0, and I'm choosing the m equals 0 state because Z is neutral with respect to rotations around the z-axis. It's just that turns out that that thing there is redundant in phi, and the m equals 0s are the only ones that contribute. That's why you only see m equals 0 in this sum. So now, let's consider what e to the ikz looks like at large R. And of course that's buried in here. The only place that the magnitude of R appears is inside the JL. These spherical Bessels, the J's, have a known asymptotic form as R goes to infinity. They behave like e to the plus ikr and e to the minus ikr with equal weights, but different phases. There it is. I put 3 lines here to help you see. The e to the minus ikr is actually buried inside the e to the ikz, inside these term by term. Second thing, where's the e to the ikr over R? Well, it turns out that J actually has a 1 over kr in it. So if you put this term and this term together, nothing more appears than e to the minus ikr over R. Okay, so that's very helpful. That's the incoming part. Here's the corresponding outgoing part. What does this thing here look like other than exactly this pair? Incoming matched with outgoing. Furthermore, notice that the phases, the magnitudes are the same. So the only thing that we notice that the J's do is that they shift, they represent a phase that's relative between these two. And if we factor out one of these, then we can see what the relative phase is by assigning this one over here to be the ratio of the two. And when I do that, I'm bringing basically this substitution and sticking it in here. Then I combine the minus side of the L with the plus side of the L, and that becomes 1. All I'm left with is a minus I, and what I can do with minus I is put it on the bottom, become plus I, and then it becomes 2ikr. So this 2kr becomes 2ikr, and all we're left with then is this whole term becomes e to the ikr. And now we're substituting into this form. So you can see the 2l plus 1 has stayed, and the p sub l has stayed. We're left with this term. Let's do it carefully. Now this time, we bring in the I to the L, and we multiply it here. These are both plus i's, and so that becomes minus 1 to the L, which I write here. I have to left over with one bachelor I that doesn't get lumped inside the power of L, and so that I have to factor out. When I bring it to the bottom, it's a plus I, so it becomes minus 1 over I, and there's the minus. Now where does this term come from? I've saturated this term, but that was only the first part of psi. So if I want to get the whole psi, I then have to put f of theta in. So e to the ikz is now expanded into this, and inside a sum over L. And now the rest of this outgoing scattering wave looks like e to the ikr over R times a sub L, and you'll remember that we had factored out the fact that the power of 2l plus 1 conveniently, so that this expression becomes simple. And in fact, the only thing that's extra in this whole coefficient is this: we don't need this 2ik. We just need the 1 over R for the outgoing wave. And so I compensate by sticking a counter term here, 2ik. That'll cancel this. And then we have just the pieces we need, 2l plus 1 A sub L e to the IKR over R P sub L. Good. So I've got an expression for the total scattering state in the region where R goes to infinity, of course, and it has this simple form. Now I want to go back to this picture and say, but there's something else we know about that. Besides this form that we inherited from the original expression for f of theta, we also know something about the relative strengths of these two, and that they're the only difference between what this guy here becomes when you just flip the sign of k is some factor e to the 2I delta. It's the only thing that controls the strengths of those two waves in this region outside A. So let's write that as a second expression. What is psi? The same psi that we talked about up here has to be a sum over L's in which each one is a little mini representation of a one-dimensional scattering from a barrier problem. Okay? Since the incoming wave is going to be the same, well, let's set up the problem with an incoming wave. Here's the incoming wave. It's identical to this one. So that means put all the numbers right beside it, just the way they were here. Okay, so I do that. I put these coefficients out front, and I put the p sub L beside it, so that my incoming wave has exactly the same strength as I had before, because I'm going to try to do a comparison between this and this expression. Then what should my outgoing wave be? Well, it should just be this one, because this is the free particle which J sub L represents when V is 0. Remember that the free particle, when there's no V anywhere in space anywhere, just is J sub L of KR times P sub L of cos theta. Since that's the free state, this would be the state, e to the plus IKR would be the state that's the reference wave. That's the one where the phase shift is 0. Okay, so we write e to the IKR. Now let's put V back in. What can V do? The worst thing it can do is advance the phase on this term. The outgoing one, just advance it by 2 delta. That's the only thing it can do. So all we do is we write the free solution and we tweak the outgoing phase by 2 delta. Boom, that's done. This expression has to be the same as this one. And when we align similar terms, we find out what A sub L can be. Let's do it. This term matches this one identically. We did it that way so that we could simplify life. That means that all the powers of e to the IKR that appear here have to equal that here. Well, here, the only thing is the coefficient e to the 2I delta. But here I've got 2. 1 plus 2ik A sub L. So those have to be equal. Comparing equal terms, 1 plus 2ik A sub L has to be this factor. Solve for A sub L, lo and behold, we end up with this expression, which tells us that conservation of probability, conservation of energy, all the things we know that are common to all potentials, tell us that no matter what the potential is, A sub L can only be of this form. Furthermore, and which is more useful than simply the mathematical constraint that A sub L has to have this shape, is that we now have some insight into what A sub L should look like, because these are physical phase shifts that we have some insight into what they represent. Remember, positive when V is attractive, negative when V is repulsive, and so on. So these kinds of interpretations and intuitions about how A sub L is constructed and what certain values mean, this is extremely useful and important as we proceed to try to use this in application to problems. So here's a summary of what I've just said. These complex amplitudes A sub L are just embodiments of the phase shift. The problem we're solving for them is simply the problem of finding the set of real numbers, delta L, between 0 and pi, or 0 and 2 pi, for any given potential. So the potential gives rise to attractive or repulsive phase shifts. The phase shifts give rise to A, and then out of those we build f of theta and the cross-section. Now there's one thing I promised to come back to, and I want to cover that here at the end. What is this potential V sub L? And I admitted to you earlier that it's different for every L, and we had actually put a subscript on the V. So how is it that the phase shifts are not the same in every wave? Otherwise, you would just you would drop the subscript L, and all the waves would be identical. Well, that's not so, because when in the problem where we reduce a 3D problem to a 1D problem, the equivalent wave function in 1D is U, and the equivalent potential you're dealing with contains the V of R plus this piece, which is the part of the kinetic term, the p squared over 2m, that gets lumped into the potential when you do that reduction. And notice that there's an L dependence here, and there's a radial dependence. This is a barrier at r equals 0. It goes to infinity at r equals 0, so therefore this represents a little short distance repulsion term. And notice that when L is 0, the S wave doesn't have any of this, so it's a pure V. And as I go up in L, the effect is to push the particle further and further away from the origin. So if you were thinking about phase shifts, and this barrier were present, then the larger the L, the further out in R towards A, you would expect the phase shifts to occur. And so as you go, you would even expect that above a certain L, the phase shift should vanish or should become very small. That's exactly the intuition I'd like you to have, that S wave dominates when the V of R is a very short range, because as you go up in L, you very quickly basically turn the particle around before it penetrates very far inside the potential enough to see the attractive or repulsive piece of V. And the further out this centrifugal barrier pushes you, the more peripheral region of V of R you're going to be sensitive to. On the other hand, a delta function potential or a very short range potential then means that only the low L waves will contribute, and the phase shifts from higher L waves will be 0. Let's try to summarize. Only the V of R itself makes the phase shift, because if this is 0, then we defined this term here, this centrifugal, to be part of the barrier. So if V of R is 0, then the reference wave is just reflecting from the barrier, and so therefore the return wave is the reference wave, and the phase shift is 0 by definition. So the old rule that we had, that delta of 0 being 0 corresponds to V equals 0, still holds. In fact, it holds in all the waves. If V is 0, then the phase shift will just correspond to the centrifugal term in all the waves, and that's by definition, the 0 phase shift. As soon as V is non-zero, it will contribute a different phase shift in every partial wave, and the fingerprint of the potential is this pattern of deltas, where the deepest part of the potential closest to r equals 0 is sensed by the S wave. Then progressively more and more emphasis on the larger R values of V as you go up in P, D, S, and so on. And you can imagine that a full string of those phase shifts are going to be a prescription for mapping out V from small to large radius. Larger L, you're picking up information about large R, the potential at large R. At small L, you're picking up the small distance behavior of V. Okay? I think that's enough for you to be able to cover the material that you need for the homework. So what comes next will be covered in 2 more lectures, and will be also explored through 1 more homework set on Chapter 11. Okay, I hope that has helped to clear things up, and what remaining questions you have, I'll take next time we're together. Okay, so I'll talk to you soon. Bye-bye.